Now, binomial probability experiments are just a specific kind of probability experiment where we have discrete probabilities. So if we have an experiment, we call it a binomial experiment if it meets these requirements. First of all, the experiment has to have a fixed number of trials. So maybe we have 5 trials or 10 trials or 100 trials, but it's not an unlimited number of trials. The second requirement is that the trials have to be independent. That means that the outcome of any one individual trial doesn't affect the probabilities in the other trials. The third one is that each trial must have all outcomes classified into 2 categories, and we usually refer to these as success and failure. So it could be something like yes or a no, on or off, defective, not defective, but it has to have only 2 outcomes. So out of our 2 outcomes, success and failure, if we look at the probability of a success in each trial, it has to be the same for each trial. When we're talking about binomial experiments and binomial probability distributions, we have some specific notation. So n denotes the fixed number of trials. This is just like us using n for a sample size. X is going to be our random variable, and for a binomial experiment or probability distribution, the x is going to denote how many successes we had in our n trials. And what this means is that the possible values for x can be any whole number between 0 and the total number of trials we had. A small p is the probability of success in any one of the n trials. So since success and failure are complements of each other, if p is the probability of success, then 1 minus p is going to be the probability of failure. And finally, uppercase P of x gives us the probability of getting exactly x successes among the n trials. Now, some hints for binomial experiments and probability distributions. First of all, be sure that the x and the small p both refer to the same category, which we're calling a success. So if you decide which of the 2 outcomes you're going to call a success, then that needs to be what the x values stand for, is how many successes there were, so how many of that particular outcome there were in the n trials, and the small p needs to be the probability of that particular outcome. Now, the independent trials requirement technically means that we have to be sampling with replacement. But if the population is large enough in the first place, then sampling with or without replacement doesn't make a significant difference in the probabilities. So that requirement where the probabilities have to be the same for each trial, if we have a large population, then if we're sampling without replacement, it's still not going to make enough of a difference in the probabilities to matter. So when we're sampling without replacement, we still consider our events or our trials to be independent if our number of trials, the lowercase n, is less than 5% of our population size. Capital N is our population size. So if we have an experiment where we know we're sampling without replacement, then we have to test and see whether our number of trials is less than 0.05 times our population size. If it is, then we can still consider it as a binomial experiment because we still consider each trial to be independent. All right, so let's just start by identifying some binomial experiments. So we're thinking about those requirements and seeing if all of them are met in some certain situations. So first of all, if a player rolls a die 7 times, on each roll the number that comes up is recorded. So we want to see whether this qualifies as a binomial experiment or not. So looking at those requirements, we have a fixed number of trials because we already know that the player is going to roll the die 7 times. So our number of trials is 7. Now the trials are independent because each time the player is doing a separate roll. So there's nothing from, say, the first trial that's going to affect any of the later trials. So that requirement is met. Now because on each roll the number that comes up is recorded, that means on each roll there are 6 possible outcomes, the numbers 1 through 6. That means that we have more than 2 possible outcomes for each trial, and that means that this is not a binomial experiment. For binomial experiment, we can only have 2 possible outcomes for each trial. So this one doesn't qualify. Now this next experiment, if a player rolls a die 7 times and the number of 6s that comes up is recorded, this is the same setup to start with. We have 7 trials, the trials are independent, and now we have only 2 outcomes for each trial because all we're paying attention to is whether the die comes up as 6 or something else. So our 2 outcomes are either 6 or not 6. So we're meeting that requirement. And finally, the probability of success, if we define success as rolling a 6, is going to be the same for each trial. It's going to be on each roll of the die, the probability of getting a 6 is going to be 1/6. So this one does meet all the requirements and is a binomial experiment. If you notice, the difference between these two is that the first one we had more than 2 possible outcomes because we were just recording the number that came up on the die. That gave us 6 possible outcomes for each trial. On the second one, we were only recording whether it was a 6 or not, and that gave us 2 possible outcomes. And we've got several methods for finding binomial probabilities. We can use technology, we can use tables, and there is a formula for this also. What we're going to do in this class is use technology, either your TI 83 or 84 calculator or StatCrunch. Now, if you don't have access to your calculator or StatCrunch, if you're doing homework or a problem somewhere and you don't have access to that, you can use the tables for some problems. You'll find tables for the binomial probabilities in the back of your textbook, or if you are using your ebook, then there's an appendix with all kinds of tables in it, and the binomial probabilities table is one of those. Now the third option is using the formula. You won't be required in this class to use the formula. You may run into some homework problems that mention using the formulas. If it says that, please feel free to use technology instead.